After watching this video lecture series, students will be able to calculate freezing and boiling points of solutions using their knowledge of colligative properties and how solutes affect the freezing and boiling points of solutions that they are members of. So colligative properties are properties that depend on the number of solute particles that have been dissolved into a solvent. And we ignore the nature of the solute particles in this context. So a few colligative properties or things that are affected by colligative properties are vapor pressure, boiling point, freezing point, and osmotic pressure. In this lecture, we're going to focus on the boiling point elevation and freezing point depression calculations. But please understand that vapor pressure can be lowered based on the presence of a solute in a solution, and osmotic pressure can also be altered. However, we will not be paying attention or calculating either of these. So again, a colligative property is a property that depends on the concentration of solute particles that are present in a solution. Freezing point depression is going to be represented by delta T sub F. And basically that's the change that is anticipated for that specific solvent's freezing point. So what will happen when we have a solute dissolved in a specific solvent is that the freezing point of the solution that's created is going to be lower than the pure solvent by itself. So if I have something like water that freezes at 0 degrees C, its freezing point is going to be lowered by the addition of a solute. In that same thought process, boiling point elevation is represented by this delta T sub B, which represents the change in boiling point. And in that context, the boiling point of the solution is going to be higher than the boiling point of the pure solvent when you have a solute dissolved into that solvent. So the equation that we're going to be using to calculate our delta T sub F and our delta C sub B is going to be generically represented by this equation. Now, depending on our constant, we're going to either be calculating delta T sub B for our boiling point elevation or delta T sub F for our freezing point depression. Okay, so delta T, guys, is your change in temperature in degrees C. And we're going to calculate that by using K, M, and I. K is a constant that you would look up in a table or would be given to you in a practice problem. Molality, remember, is calculated by taking the moles of your solute divided by the kilograms of your solvent. We know how to calculate that, plug that into there. And your Hoff factor is your number of particles, and we're going to discuss how to determine those numbers of particles. So figuring out the Hoff factor, or the I value, is going to correspond to whether you have a covalent or ionic compound in your solution. So what ends up happening is when you place a non-electrolyte or a covalent compound into a solvent, what happens is that the solvent completely surrounds the solute, and the solute doesn't get broken into any simpler pieces, so they remain intact when they're dissolved. So when we are counting up the number of particles coming from the non-electrolyte, we count that as being 1 particle. So my Hoff factor, or my I value, is going to correspond to 1 for non-electrolyte covalent compound. Now, when looking at electrolytes or ionic compounds, what happens when we place them in solution is that the ions that compose this ionic compound get broken into their corresponding ions. And those ions, as we see here to the right, get surrounded individually by solvent molecules. So the number of ions that are present in a specific ionic compound, as we see here, are going to dictate our I value for our Hoff factor. Okay, so NaCl consists of 1 sodium ion and 1 chloride ion, so I is going to equal 2. Barium chloride consists of 1 barium 2 plus ion and 2 chloride ions, so I equals 3. And so on and so forth. You can see the more ions you have present in the ionic compound, the larger your Hoff factor value. Okay, so in this problem here, they want us to find the freezing point of a saturated solution of sodium chloride containing 28 grams of sodium chloride in 100 milliliters of water. And they told us that the freezing point constant, or our K value, is 1.86 degrees C times kilogram per mole. Okay, so we know we're going to be using this delta T equals KMI. We have our K value. Okay, we have the information that we need to calculate I. Okay, and we have the information we need to calculate our M value, okay, or our molality. Okay, so our I value here is going to equal 2. The way I know that is because sodium chloride is an ionic compound. It consists of a sodium ion and a chloride ion, and since there's 2 different ions in the compound, I will equal 2. Now, in order to calculate our molality, we're going to need our moles of solute as well as kilograms of solvent. So we're going to go ahead and calculate our moles of solute. And if we go ahead and divide by our molar mass, we end up with 0.4792 moles of sodium chloride. So we see that here. Okay, and so now we need our kilograms of our solvent. So we need to take our 100 milliliters of water and convert that into kilograms of our solvent, since water is our solvent. Okay, if we go ahead and carry out that calculation, we use density to convert our milliliters into grams, knowing the density of water being 1 gram per mil, and then using our relationship between kilograms and grams to calculate our kilograms of our solvent. Okay, and then we're going to go ahead and plug both of these into our molality calculation. So if we go ahead and we divide those, we end up with 4.792 moles per kilogram for our molality. All these values now are going to get plugged into our equation here. And our calculation here for our delta T sub F is going to give us 17.82 degrees C, if we go ahead and do a unit evaluation. Okay, so this is our delta TF. So this is our freezing point depression. This is how much it changes. Now the question asks us to calculate the freezing point of the solution. Okay, so delta TF is not the freezing point, it's the change in the freezing point of the solvent. So we need to take an additional step and go ahead and calculate our freezing point of our solution by taking our freezing point of our solvent and subtracting out our delta TF. So since our water is our solvent, 0 degrees C is going to be our original freezing point, but then we're going to subtract out that 17.82 degrees C, and this is going to give us negative 18 degrees C as the new freezing point of our solution. So in this practice problem, they've told us that they want us to find the boiling point of a solution that consists of 0.73 moles of glucose, which is our solute, and 225 grams of phenol, which is our solvent. Okay, so we're going to be using the following equation. Our delta TB equals KMI, and so we need a few pieces. Obviously, we need our K value. Our K value is going to be determined, obviously, by the constant that they've provided here. So this is our K. They have given us information to calculate our M value, and they've told us that glucose, which is sugar, is our solute. So because it's a covalent compound, our I value here is going to equal 1. Okay, so we need to figure out our M value. Okay, and remember, our M value is going to be equal to our moles of solute divided by our kilograms of solvent. So now that we have that relationship there, we're going to go ahead and plug in our values. So we've taken our 0.73 moles of glucose and divided it by our kilograms of phenol. So notice we've converted our grams of phenol to kilograms. And this is going to give us 3.24 moles per kilogram as our molality. So now we need to go ahead and plug these values into our equation here. So now that we've gone ahead and plugged those in, we're going to go ahead and put those in our calculator, and that's going to give us 11.66 degrees C. Okay, and so we're going to go ahead now and calculate the temperature at which the solution is going to boil. Because remember, our delta T sub B is only the change in boiling point of that solvent, not the actual solvent's boiling point. So we have to consider the boiling point of the solvent. And we see that in this equation here, the boiling point of the solution considers the boiling point of the solvent, but we add our change in boiling point from our calculation up here. So in this context, they have not given us the boiling point of our solvent, which is phenol, so that's something that you would have to look up. However, in any quizzes or tests, anything other than water being your solvent, the boiling point or the freezing point will be provided to you. So You need to know water's boiling point and freezing points, but other solvents, that will be provided. Okay, so if we go ahead and we look up the boiling point of phenol, we find that it's going to be 181, 1.7 degrees C. Our delta TB is as follows. Okay, and if we go ahead and we sum those together, our new boiling point is going to be 193 degrees C for that phenol and glucose solution.